How do you find the direction of a vector? You will have to find the unit vector by dividing this vector by its magnitude, that is normalizing it. When you are seeking gradient from a scalar field, you are actually migrating to a vector field. Now I need to find the value of this along this particular vector. That means I am literally projecting this vector onto the direction of this vector. How do you find the direction of a vector? It is as simple as that. If I say that this is my n hat and this is my gradient vector, when I project it, so this is theta, what I get here is this f. Now let's look at one more typical situation of the model question paper. Now let's try and understand what exactly it needs to solve such a problem. What is expected here is the directional derivative, and the direction is characterized by a vector. That is, in the direction of this vector, if you are seeking the derivative of this particular function, what would be the value? And in order to solve this particular problem, we'll recall the introduction to gradient. What did we say? Gradient gives you the maximum derivative, directional derivative, which is of course perpendicular to the tangent at that point to a curve, or the tangent plane. It becomes normal to the tangent plane if you are talking about a surface. Now here we are trying to seek the directional derivative along a certain vector. That means you are not seeking the maximum directional derivative, which is of course the gradient. Here you will have to find the gradient and then take the projection of that gradient onto this direction. It should be very, very clear. That means if you are seeking the derivative value in certain direction, then you will have to first find it, which is nothing but the gradient, and that gradient's projection, that is, the gradient is also a vector, that should be projected onto the direction of this vector. How do you find the direction of a vector? You will have to find the unit vector by dividing this vector by its magnitude, that is normalizing it, and then you will get a direction onto which you should project your gradient, so that you get the value of directional derivative. So let's try and do this problem. What would be the first step? First step would be to find the gradient at this particular point, which would be a vector with certain magnitude, and then that vector will be dotted with the unit vector which is along this vector. That means the unit vector is got by dividing this vector by its magnitude, and if you take the dot product between the resulting gradient at this point and the direction of the given vector, then you are done with your problem. So let's go systematically. So first let us try and find the gradient. How would you find the gradient? So the gradient is defined as follows. First you are going to differentiate the function partially with respect to x, so that forms the ith component of the gradient. Then you are going to seek the partial derivative of the function with respect to y, which forms the jth component, and then you are going to seek the partial derivative of the function with respect to z, which forms the kth component. So your vector, your gradient is done. So this gives the greatest variation of the function, or the scalar potential, because in physics generally the symbolism phi or phi, whichever way you'd like to pronounce it, is used to represent the potential function. For example, it can be gravitational potential, electrostatic potential. So therefore when you take the derivative of that particular potential, you get a vector field. That is, when you are seeking gradient from a scalar field, you are actually migrating to a vector field. So that is why it is the potential derivative which is the gradient, and that gives you the direction of greatest variation of phi and also the magnitude. So now how do you go about finding it? differentiate x square yz plus 4x z square with respect to x first. There are two terms that contain x, so therefore it's going to be 2xyz. And then what about this? There is one x, so it becomes 4z square, and this goes to form the ith component. What about the next component? Look for the term that contains y, and that is only the first term, so therefore the kith component would be simply x square j. And what about the kth component? Because both these terms contains z, so therefore what happens, the kth component would be x square y plus 4. If you differentiate z square, it becomes 2z, and then it is going to be k. So this goes to form the gradient of the function, and this is the vector that gives you the direction of greatest variation of the function, and the magnitude will give you the rate at which it is varying. So now if I substitute x for 1, y for -2, and z for 1, I'll get the following. Because y is -2, x and z are 1, so it is simply -4. Because wherever x and z are there as multiplicative factors, they are simply replaced by 1, and y is replaced by -2. And what about the next term? It's simply going to be 4. So therefore what happens, in fact the first component goes to 0. And what about the next component? It's simply x square z, so therefore this is simply going to be 1, because both x and z are 1. And what about the last term? The last term, the first is -2, the second term is 8 plus 8, so therefore this is also got. So what we have here is j minus 2 plus 8, that means plus 6. So this becomes your gradient, right? This becomes your gradient. Now I need to find the value of this along this particular vector. That means I am literally projecting this vector onto the direction of this vector. How do you find the direction of a vector? It is simply the vector divided by its magnitude, right? So therefore if I have the vector 2i minus j minus 2k, this is my vector, and the unit vector whose direction coincides with this vector is simply given by its magnitude, which is 4 plus 1 plus 1, that is 2 square plus 1 square plus 2 square. So this is 8 plus 1, which is 9, and therefore what happens, you get 2i, because square root of 9 is 3, so this is 3 minus j by 3 minus 2 by 3 k. All right, so this is the unit vector that whose direction is along this vector. Because I want to project my gradient onto this direction, I will just have to take the dot product, right? So what I am trying to do is, if I say that my gradient is f, let us say my gradient is f, and if I designate this as n hat, that is a certain unit vector, then all that I am requiring is this. This gives you the projection of f onto this. So how would we go about this? This is given by magnitude of f, magnitude of 1 into cos theta, right? So this actually gives you the magnitude of the gradient multiplied by cos theta. It is as simple as that. If I say that this is my n hat and this is my gradient vector, when I project it, so this is theta, what I get here is this f cos theta. Isn't that very, very clear and obvious? I have got my n, and I have got my gradient here is j plus 6k. All that you got to do is just take the dot product and you are home. So let's complete that formality. So what is my gradient vector? It is j plus 6k, right? So this is let me designate it as f. And what about my unit vector along that vector? It is 2i by 3 minus j by 3 and then minus 2k by 3, right? So if I take the dot product, so whenever you are taking dot product, remember you are taking the product of corresponding elements, ith, jth and kth. But unfortunately here the ith element is absent, that is 0. So you don't get 0. You in fact get you don't get the first element, that is 0 into 2 by 3. And then what about the next one? You have plus 1 and minus 1 by 3. The coefficient of j here in gradient is plus 1. In that of the n unit vector, that is unit vector n, is minus 1 by 3. So it's going to be simply minus 1 by 3. And what about the kth component? It is 6 for the gradient, and for the unit vector n it is minus 2 by 3. So it's going to be minus 6 into 2 by 3. So this is your dot product, that is f dotted with n, which is the required value of the directional derivative. Okay, value of directional derivative, right, which is nothing but the projection of the gradient onto this direction. So what this simplifies to be, so this is going to be minus 12 by 3 minus 1 by 3. So this is minus 13 by 3 is the value of directional derivative. So all that I had to do was just find out the gradient, then find out the unit vector along the given vector, that is the direction of this particular vector, which is the unit vector along that vector, which is called n, and then take the dot product, which is physically, if you see, if I say that this is my gradient and this is my n vector, that is the direction of the given vector, that is the unit vector, then if I take the dot product, that will give me the projection of the gradient onto the direction. That means how much is the derivative along this direction, that is what physically I am seeing. The direction along the gradient direction is maximum, but about some other direction, what is the value of derivative, how fast the function is changing along this direction. That's what exactly it is sort. That is why when theta becomes 0, you can clearly see that what happens, the directional derivative becomes maximum, because the maximum value of cos theta, because if I say n is fixed, f is fixed, the theta value is 0 when this product or this dot product becomes maximum, that is cos 0 is 1, maximum value of theta is 1, and that is where if theta becomes 0, then what happens, the maximum directional derivative becomes the gradient itself. Okay, the maximum directional derivative becomes gradient itself. So what we have found is the value of the directional derivative, the value of the derivative along this direction. So this is what is the solution. So let's move on and look at more discussions, but importantly what you should not forget here is that how to find the gradient. This is the standard formula, very simple. So first differentiate with respect to x, then differentiate with respect to y, then differentiate with respect to z, and then evaluate at a given point, and also very interestingly, once you find out the gradient, that is partially differentiate with respect to x, y, z, substitute the values and numerically get the value. So if you try to divide this by its magnitude, this is nothing but normal to the tangent plane that is drawn to this particular function at this particular point. Remember that. Okay, so that normal gives you the direction of maximum directional derivative. But if it is sought about some other direction, then normalize that vector, divide by that vector by its magnitude, so that you get the direction of that particular vector onto which you are projecting your gradient, that is you are taking a dot product. That means whatever you are getting is the value of the derivative along this direction, along that direction. So Therefore, it is all about projecting your gradient onto certain direction, and also when theta is 0, you get the maximum value of the projection. That means the gradient itself, the value of the gradient itself, or the magnitude of the gradient itself, gives you the value of greatest directional derivative. So let's move on and look at more discussions. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.